In this demonstration, we're going to show how, with sim events, you can explore manufacturing production processes. In this case, the manufacturing process is a chemical batch production process, which has shared resources. You see such processes used in the manufacture of pharmaceuticals. However, this model more generally helps us explore resource allocation problems. We've chosen to model this entirely as a discrete event system for demonstration purposes. However, with other MathWorks products, we could have made a hybrid system with continuous time dynamics. Let's take a look at the SimEvents model of this system. The order system generates orders with different demands on the production resources. The production system is assigning reactors to a particular order and then processing the order. The process analysis piece displays how the chemical production process resources were used over time. Let's dig in and look at the major components. The production orders subsystem simulates the generation and backlog of two types of production orders, an A and B batch, and then holds the order in a queue until a reactor is ready. You might imagine the A batch being a weaker strength of a particular pharmaceutical and B being a stronger one. They each would require different amounts of time of the shared resources available. Batch reactors is a resource pool block that defines the batch reactors used in the model, one of the main shared resources in this production process. One reactor is used to process one production order or batch. Once a particular production order is received, the block labeled Obtain Reactor requests a reactor from the resource pool. This begins the chemical process. Inside the Execute Chemical Process Recipe subsystem, there are a number of manufacturing steps, such as adding water, heating the mixture, adding color and particles, agitation, and draining. Once the chemical process recipe is complete, then the batch reactor is released to be used for another order. The data analysis subsystem analyzes data related to the completion of the production orders. Upon simulation of this model, you can inspect different simulation output results and system characteristics, including the utilization of different resources, average order backlog, or throughput. For the example right now, we can observe that the utilization of batch reactors is pretty high, and there is a backlog of over 80 orders at the end of the simulation. Maybe we need to invest in getting additional resources to improve the production rate. We can alter the resource profile in different ways and observe the changes in simulation results. This will help you better understand how to allocate resources to account for different usage scenarios. For example, you can change the number of batch reactors, water supplies, heaters, and drains to see its effect on the overall production process and throughput. Let's increase the number of batch reactors and look at how this changes throughput. As we can see, the backlog has decreased from over 80 to under 60. You can also change the configuration for a specific batch or chemical recipe in terms of how a specific order utilizes these resources. In this way, we can simulate various what-if scenarios to analyze the manufacturing process. We can extend this model in a number of different ways. In the video Optimizing Manufacturing Processes, we demonstrate how to use this model and MATLAB optimization to best allocate resources. You could add multiple batch types, pull in actual recipe data from MATLAB, or simulate the dynamics of particular production steps using Simulink. In summary, this simple example illustrates how you can use sim events to model a manufacturing process to identify bottlenecks that need to be addressed for efficient production.